Hi. In the last video, we went through the idea of the cost for motion, which was force. Right? We went through the natural state of an object, which is either it can be in motion. If it is already in motion, it will continue to be in motion, and if it is at rest, it will continue to be at rest. And this was Newton's first law. And then we quantified the force, which was like force was equal to mass times the acceleration, which was Newton's second law. And then we also went to the third law of Newton, which was the aspect of force always occurs in pairs. There is always, for every action, there is always an equal and opposite reaction, right? So in this video, we will go through one natural force, right, that occurs around us, right? So in the earlier chapter, we spoke about external intervention in the form of we either push or pull an object, right? So that is how we allow an object to get into an influence of force. But without any external intervention, there is a very fundamental force around us, and that is the force of gravity, right? And that will be our focus in this video. So let's get started. Okay. So when you talk about gravity, the first thing that is likely to come to your mind is Newton's observation of the fall of an apple, right? So let's see that what really happened. Let's put ourselves in the shoes of Newton and see what would have gone through in Newton's mind. So primarily, right, one thing, there are two things that is likely to have intrigued Sir Isaac Newton. One is the fall of the apple, as we all know, right? That is what prompted Newton to explain the force of gravity. The fall of apple always happened. I mean, the first aspect that is likely to have intrigued Newton is that why is it that the apple always took a path that is perpendicular to the surface of the earth? Why doesn't it take any other path, right? When it has to fall from the apple, that was likely to be the first thing that is likely to have intrigued Newton. The second thing that Newton was also intrigued about is the aspect of the movement of the planets, right? So we have the sun. Right, we have the sun and we have the earth revolving around the sun, right? Let's consider this as the earth, and surrounding the earth we also have the moon that is revolving around the earth, right? So all these were also kind of intrigued Newton, and he wanted an explanation as to why objects revolved around another object. Right. So there are two things. One is, why does the apple always take a path that is 90 degrees to the earth? In fact, it takes the shortest path. Right. If you really see from the tree, the apple always takes the shortest path towards the earth. Second thing is, what makes objects revolve around other objects, like the earth that is revolving around the sun and the moon that is revolving around the earth, and there are a lot of other moons around other planets, right? So all these he wanted an explanation for, and that's when he performed this brilliant thought experiment. I say it as a thought experiment because it cannot be this experiment that I'm going to articulate is something that you obviously cannot do it in real world, but it gives enough ideas to think about the underlying cause for gravity, right? So that's why, I mean, you cannot really experiment it in a lab, but you can think about it, and that will help you explain the behavior of things around us. So that's why we call it a thought experiment. So the thought experiment is called the cannonball experiment, Newton's cannonball experiment, and the experiment goes like this. So Newton wanted us to imagine a big hill, a tall hill on top of the surface of the earth. So I'm going to draw the earth something like this, right? This is the surface of the earth, and there is a tall hill on it. And what he suggested is what he wanted us to imagine is he think about a cannon that is placed on top of that hill. A cannon can shoot bullets, right? Right, and use that at times of war, right? And what Newton proposed was, okay, if you place a cannon on the top of a hill and if you shoot, what is likely to happen? Say if it obviously the bullet or the cannonball is going to be released with a huge force, a much higher force. So it will travel a certain distance that is, parallel to the Earth, and then eventually it will fall, right? It will yield to the force of gravity, and it will fall here, right? So somewhere here. Now, what if you shoot? Now, what if the cannonball you apply even additional force to the cannonball from the cannon? What will happen? So obviously it is likely to go even further distance, and it is going to fall at a slightly farther point, which I'm calling it as B here, right? So this is what you see here is with a certain velocity in which the cannonball was thrown, and here we have applied an even higher velocity, and it is covered a certain other distance, a higher distance. Now the thought experiment, and here is where Newton's brilliance comes into play. He wants us to imagine where you fire it with a very high velocity, right? Something that is hard to imagine, extremely high velocity. What is likely to happen? So if you really think about it, now I'm going to draw the hill in a hill out here, and let's say this is how the cannon is, and it fires, right? And it fires what? So it's going to take a fairly long time because you're firing it with a very high velocity. The ball is going to take a very long time to start giving you this bend and start falling towards the Earth, right? So the point here is it would travel for the velocity is so high that it travels for a very long time, and by the time it starts to bend, right? By the time it starts to bend, what would happen? Because it would take for a very long time. It's only after a long time that it would start to fall, right? So let's say that it takes a fall here, right? It starts to yield to gravity at this point in time here. Now it would have taken a long time to reach this point because it was fired with a very high velocity, right? So by that time, what would happen is the Earth is also not flat. The Earth is also curved, right? The Earth is curved. And the Earth is also rotating, right? So which means that the Earth would have, moved away. So the distance between the cannonball here and this particular distance would be more than the distance here, right? D1 must be less than D2. Right, because of the Earth's curvature, the cannonball would have reached a point wherein from which it has to travel for a longer distance to fall on the surface of the Earth. Right. Now, what is also likely to have happened is at this time the Earth would also be moving in. Right. So the Earth's curvature would also continuously increase. Right. Because because the Earth is also moving. Right. So which means that. So if you think about it, the cannonball here has to travel for a longer distance, and by the time it covers this distance and comes in here, the Earth's curvature would have moved somewhere like this, right? It would have become somewhere like this because the Earth is also moving around the Sun. So which means that by the time this cannonball covers this distance, you would have the Earth's curvature and the movement also would have created an additional distance. So what will happen is that at certain velocity, if you fire, which is very high, the ball will continuously try to fall on the Earth. And how it will appear to somebody on the Earth is that it will revolve around us, right? And that is how he was able to explain the phenomenon of the moon revolving around us. The moon is really not moving. The moon is trying to constantly, it's actually trying to fall onto the Earth. Because of course, the moon was not fired from a cannonball, but the behavior of a cannonball is how the moon is how he was able to explain the behavior of the moon. The moon is always trying to fall onto the earth, but the earth is also moving, and thereby for every 1 meter, if it tries to fall, the earth creates that additional 1 meter, and so the moon is always on the same place, right? Now it is at this moment that he was able to explain the behavior of gravity. Now, what he felt was, any two objects, so be it the moon and the earth, or earth and the sun. He proposed that every object attracts another object, right? That is a very fundamental law of nature. Every object attracts another object, be it big or small. It attracts the other one. And when two objects attract one another, of course there will be an influence of force in between, right? And he said that as long as the objects are close, the force is going to be high, and as long as the objects are far away, the force is going to be less. And that is the reason why the moon is fairly far, right? Moon is fairly at far from the earth, and that is why its influence the influence diminishes, because it is far from the earth. The apple is very close to the earth, and that's why it immediately falls and hits the earth. The force is high, and it immediately hits the earth. Objects that are very far, it is not as high that it is able to attract, but it is still there is still a force of attraction that it is not able to completely go away, and that is why the moon is rotating around the earth and revolving around the earth, and the earth is also revolving around the sun, because the earth is attracted by there is a force that exists between earth and the sun too, right? So what is that force? He proposed that force is directly proportional to two things, proportional to the mass of both, product of the mass of both the objects. So if the mass of the object is high, there is a higher influence of force. And if both the objects are of high mass, then the force is very high. If one of them is small and one of them is high, still it is, the mass is high. And if both of them are small, the mass is low. So the force is low. So the force is directly proportional to the mass, product of the mass of both the objects, and the force is also inversely proportional to the square of the distance between them. Because as we just saw, however big the objects are, if they move away from one another, the force diminishes, and that is the reason why the moon is at a very far distance, and that is why the influence has diminished, and it has enough force just to keep falling towards the earth, and in a way it keeps rotating around the earth, right? So this is how Newton, this is what Newton proposed, and through this he was able to explain everything, right? Everything fell in place with this understanding, right? That force is always proportional to the product of the mass of both the objects, and it is inversely proportional to the square of the distance between them. So you consider two objects here. Let's call it M1, and let's call this one M2, right? And from the center, right? The distance is measured from the center of that object. If this one is going to be D, now both of them will the force is going to be across between both of them, and that force, right? That force, if we call it force F, so force F is directly proportional to M1, M2 divided by D square. So this is the relation that he proposed, and he also he derived with this, he was able to experimentally, right, after many years after Newton proposed this was experimentally validated on a lab setting, and which meant that your whole equation becomes like the force can be equated through a constant, and let's call it G, M1 M2 by D square, and this G is called the universal gravitation constant. Universal gravitational constant, and this is the universal law of gravitation. this is Newton's universal law of gravitation, and this G is called the universal gravitational constant. So when Newton proposed this, he proposed this formula, and years after him proposing this, it was validated, and it was indeed found to be true in a laboratory setting. And G has a value, which we will soon see. The G has a certain constant. Experimentally, it was determined that G has a very, very specific value, and we'll soon be using that in some of the problems here. Right. So this is the. I hope this gave you an intuition of how Newton stumbled upon this universal law of gravitation, and how he was able to explain the phenomenon of the moon revolving around the Earth, and the Earth revolving around the Earth revolving around the Sun. So how does it explain the phenomenon of the apple falling on the Earth? If you apply the Newton's law of gravitation, right? So universal law of gravitation, apple is one object, so it's considered as M1, and Earth is a huge Earth is a huge object, right? So obviously, there is going to be a force of attraction between the center of the apple and the center of the Earth, right? So there is always going. So if you consider this to be the distance, and if you consider this to be the center of the Earth, and this to be the distance d. So, per Newton's law of gravitation, the force is going to be equal to g of the mass of the apple times mass of the Earth divided by d square, right? So, and this applies there also. So it is this force that is acting on the apple, and because the apple the force is acting on both, right? It's not just that the apple is falling on the Earth. You can also the Earth is also falling on the apple. Just that the apple's mass is less, so that is why the apple ends up moving towards the Earth, right? So the force is actually acting on both. The Earth is also acting on the force is also acting on the apple. The Earth is the Earth is also trying to fall on the apple, as well as the apple is also trying to fall on the Earth. The only thing is that because the apple's mass is small, the apple ends up moving, right? The Earth doesn't move. Same is the case. Whichever the smaller object, that tends to move. Like between the Earth and the Moon, there is an attraction between both, but Moon tries to keep falling onto the Earth, and it ends up as if it is rotating or revolving around the Earth, because that has relatively lesser mass. Same is the case if you take between Earth and the Sun. The Sun's mass is even higher, so that's why the Earth tends to move around the Sun or revolve around the Sun. So, given this, let's talk about one aspect of this force. So, if you really see this thing, right? I mean, if you think about this, let me use a different color. So you have the Earth. Let's say you have the Earth out here, and you have the Moon. Right, and the Moon revolves around the Earth. It takes a circular path, right? Let's say it takes a circular path like this, and it means that the Moon constantly looks. I mean, the Moon takes such a path around this, and at every point the Moon is trying to fall on the Earth, right? So, which means that there is always, the force is, it is attracted. The Moon is always attracted towards the Earth. So the direction of the force is, although it takes a circular path, and it actually tries to, fall on the Earth at every point in time, right? So we call that force, we call such a force as, centripetal force. It's called centripetal force because it is the force that is acting on that object is seeking the center, right? It is the Moon is actually seeking the center of the Earth, and it continuously it keeps trying to fall, right, come towards the Earth, right? So it is a center-seeking force, and that's what you call objects that that have this behavior of taking a circular path with with the focus of with wanting to come to the center, we call those objects to be under the influence of a centripetal force. And you will see this action in many scenarios. Like if you really take if you tie a stone onto a string, and then if you rotate that string around you, right? So something like this, right? So you're here, and then you have tied a you have tied a stone to a string, and if you try to rotate around you, it will take this path, right? And it means that the stone continuously tries to seek the center, and that's how it takes a circular path around you, right? So the force, it is under the influence of a centripetal force, right? Now, one thing to complement that is, so if there is a force, if the object, if the stone tries to seek the center, or if the moon tries to seek the center, we know from Newton's third law that a force always occurs in pairs, right? So if there is one force, there must be an equally an opposite force that is acting on that particular object, right? So in this case, if the moon exerts a force towards the Earth, and if we call that centripetal force, the Earth should also there should also be an opposite force that will be acted on the moon, right, by the Earth, and that is Newton's third law, right? That is the reaction on top of that Earth, and that force is called centrifugal force. We might learn this all in the other grades or classes, but the opposite of this, the reaction part of this is called centrifugal force. And you can really see this in action. You can really see this in action when if you are in a merry-go-round in a festival, or in a gathering, right? In a merry-go-round, if you really see towards the end, while each of the compartment, it all takes a circular path, you will see that when you are on a particular object, right, and when you go on a merry-go-round, you are likely to move away from the center as well, right? So that is you are under the influence of that centrifugal force, right? You still go away, but you still continue to come around the center, right? So when you are in a merry-go-round, if you are if you are starting here, right, and you take a circular path around this, over a period of time, you will end up be coming here, which means that this is the reaction force that acts on you, and you tend to go away as well, right? But overall, at this point, this is still center seeking, but there is still a force, that pushes you away as well. So these are the two parts, the centripetal force and centrifugal force. So this is the action and the reaction aspect based on Newton's third law. So let's stop here, and we will take this further in our next video.
One final thing before you leave. If you wish to revise the concepts that you've just learned, please look up and try out the free Revise app bot on Telegram app. Telegram is available for free on both iPhone and Android. Also, if you did like the content that you just watched, please do like, share, and subscribe this with your friends. Thank you.